Hey everybody, welcome to the Chapter 6 guided assignment. So Chapter 6 is over continuous probability distributions. So the first problem covers the uniform probability distribution. We can tell because it tells us in the problem right here, or in the problem title, but recognize that on the exam, you won't always have those problem titles. So you need to figure out how to tell what type of distribution it is from clues in the text of it. For this one, it tells us that X is a random variable that is uniformly distributed between 10,000 and 15,000. So that helps us. And so anyway, so that's kind of how we can tell on this one. Other times we have to learn clues. Remember that the best clue for a uniform probability distribution is just that it's that, like that the variable X will be uniformly distributed, whether or not it says that, but typically it will say that, but between some lower and upper bound, like this says between 10,000 and 15,000. Okay, so it says, suppose you bid $12,000. What is the probability that your bid will be accepted? So to figure these out, really what we have to do is sort of break this down into how these bids could go. Okay, so it says that the seller has announced the highest bid in excess of $10,000 will be accepted. So we could have a bid of somewhere between 10,000 and we'll say 10,999. Or we could have a bid between 11,000 and 11,999. Or 12,000 to 12,999. Or 13,000, 13,999, or 14,000 to 15,000. Okay, so those are our options. The bid could fall into any of those categories, especially since it's telling us like all of these are in round numbers. So it says, suppose your bid is $12,000. So if I bid $12,000 and these are truly uniformly distributed, it really means that since there's 5 categories here, there's a 20% chance of any one of these happening. So if I bid 12,000, then really what I'm saying is there's 2 times 20% or a 40% chance that my competitor will bid less than me. So the probability my bid will be accepted, which really means the probability that my competitor will bid less than me, is 40%. So when it's uniformly distributed, it means, whoops, we're going to say this is a number. That means there's an equal chance of any of these happening. So then to find the probability of less than a given point is just the sum of the probabilities of the points below it. All right, so suppose you bid 14,000. What's the probability your bid will be accepted? So if I bid 14,000, then there's an 80% chance for 0.8 that the other bidder will bid less than me, so mine will be accepted. So what amount should you bid to maximize the probability you get the property? Honestly, if we bid 15,000, that means our probability of getting the property is 1 or 100%. So bidding 15,000 is going to maximize our probability that we get it. Okay, it may not be the best move financially, but if our primary goal is getting it for sure, then that might be our best option. So part D says, suppose you know someone is willing to pay you $16,000 for the property. You are considering bidding the amount shown in part C, but a friend suggests you bid $13,000. If your objective is to maximize expected profit, what is your bid? So expected profit, it makes it sound like it's what we would expect to make. So I would think, oh, if I spend 13 and I sell it for 6, my profit would be 3,000. But the term expected profit has to do with the amount of profit we believe we'll make, but that is factored against the probability or likelihood that we would actually make it. So here's how we do. So I'm going to do selling price. So if we sell it, we would sell it for 16,000. And then our purchase price, which is what we're trying to figure out is the best one, could be anywhere between 10,000, 11, oops, I'll do 1,000. And actually, it can't be 10,000, right? Because it says in excess of 10,000. So we're just going to get rid of that one. So our sales price minus our purchase price is the profit we would make. So if we could purchase it for 11,000, we'd make a profit of 5,000. If we could purchase it for 12, 4,000. Then we have the probability of actually getting it. So 0.2, 0.4, 0.6, 0.8, and 1. So our expected profit then is just going to be the profit we would make from a given sale times the probability of that sale. So we can see that that bidding 13,000 would actually maximize our expected profit. So we really should bid 13,000. What's the expected profit if we bid that? It's 1,800. Remember, don't get confused by this, because if we were to buy it for 16 and sell it for buy it for 13 and sell it for 16, we would make a profit of $3,000. So recognize that expected profit is just a mathematical construct. For any one given thing we might buy and try to sell, of course, we're going to focus on what we would actually make. But if we're in a business that buys and sells these pieces of land, and we're going to do 1,000 of them in a year, we want to maximize our expected profit, even though that means sometimes we won't get the land, right? Because we bid too low or whatever. So expected profit's a mathematical construct to help us maximize our overall profit, especially over, say, a large volume of transactions. So I'm going to check my work, make sure I did that right. Looks like I did. So we will move on to the next problem. All right. So the second problem is a normal probability distribution. It says, given that Z is a standard normal random variable, compute the following probabilities. So remember that standard normal distributions mean that we're using Z as our units, okay? And Z is standard deviations away from the mean. So like the first one, it says, what's the probability that the Z is greater than negative 1.98 and less than 0.49? Okay, that's really what it's asking us. And so to do that, since we're working in this sort of standardized format, we use the function norm.s for standard.dist. Okay, so that's the function we're going to use. So here's how I set something like this up. I kind of create a little calculator for myself, and I'm going to say the high Z score, and then like the low Z score. And so, which means like on A, the high Z score is 0.49, and the low Z score is negative 1.98. Then I'm going to find the probability of getting that Z score. So to do that, I'm going to use equals norm.s.dist. And all I have to do is put in my Z score, comma, true. Whenever we put in true, we're saying, give me the probability of getting this Z score or lower, okay? So a Z score of 0.49 or lower has a probability of 0.6879. So 68.79%. Now I'll do the probability of my lower z-score. And there's only a 2%, 0.02385 probability of getting a z of negative 1.98. So here's the cool thing. If I measure what's the probability of getting less than 0.49 and the probability of getting less than negative 1.98, if I subtract the two, that gives us the probability that it's between them. So if I say probability of the high minus the probability of the low, gives me the probability that it's between. And then this wants me to do it to 4 decimals. So I'll do that. So the reason I set it up like this is because now I have a little calculator for myself. And all I have to do is update my z-score. So on B, my high z-score is 1.22 and my low z-score is 0.52. And now I see my probability between is positive 0.1903. Probabilities are always positive. Remember, they're between 0 and 1. Finally, on part C, my higher z-score is negative 1.04. And my lower z-score is negative 1.75. So the probability that it's between those two is 0.1091, or about 10.91%, right? So I'll check my work. Hooray. So remember, when we're working in z units, which are standard normal units, then we're going to use the function norm.s.dist, which stands for a normal standard distribution. All right, on to number 3. So here we have automobile repair costs continue to rise with an average cost now at $367 per repair. Assume that the cost for an automobile repair is normally distributed with a standard deviation of $88. Answer the following questions about the cost of automobile repairs. And so here's all our questions. So here we're still looking at a normal distribution. Again, it tells us they're normally distributed. But we're not working in z units now, right? We're not working in standard deviations. We're working in dollar units. Okay, so I know that I have my average or mean cost, which is 367. I also know that I have a standard deviation of 88. And then I'm going to have some value that I'm checking on. So this one says, what's the probability the cost will be more than 450? So I'm going to call these variables that they're going to throw at me X. Okay. So remember, when we use the function, so for whenever we are working on normal distributions, and we're trying to find the probability for some value of X, we're going to use the function equals norm.dist. So not S for standard, just norm.dist. And there we have to include our value of X, comma, our standard deviation, comma, and, our mean, and then our standard deviation. Our mean, comma, and then our standard deviation. And then for cumulative, we're going to say true. So this is going to return the probability that given a mean of 367 and a standard deviation of 88, then what's the probability that X is going to be 450 or less? So remember that with probabilities, that probabilities are somewhere between 0 and 1, and that all probabilities have to add up to 1 or 100% chance of something happening, okay? So if I say 1 minus the probability that it's less than something gives me the probability of it being more than that, okay? And so the probability that the cost will be more than 450, so I'm looking for more, is going to be 0.1728. Again, it wants my answers with 4 decimals. So I'll do that. Probability that's more than 450 is 0.1728. What's the probability that will cost less than 250? So now I can just change my X, and the less than is 0.0918. What's the probability that it will cost between 450 and 250? Okay, so a couple ways I can do this. I could change this to 450 and look at the probability that it's less. And I'm going to copy that and just put it over here for a minute. Then I'll change it to 250, and I'll take the probability that's less and find the probability that it's between. I can just take the probability that it's less than 450 minus the probability that it's less than 250. And that'll give me the probability that's between, or 0.7354. Finally, it tricks us a little bit here. It says, if the cost of the car repair is in the lower 5% of automobile repair charges, what is your cost? So we'll be looking at all this data and we'll be like, I don't know. And we could, if we wanted to, we could like keep tweaking this number here until we got this down till we got the probability that it was less than at 5%. Or whenever we're given a probability and we're trying to find a value of X, remember norm.dist is how we get a value of X, and we're trying to find a probability. So when we're given a probability and we're trying to find a value of X, we're going to use a function called equals norm.inv for the inverse of normal. There we put in the probability. So 5% or 0.05, the mean, comma, and the standard deviation. So this will tell us what value of X would be the value where 5% was at or below that. And the answer is 222.25288. It tells us to round to 2 decimals, so 222.25. Check our work. And hooray, we got it. All right, so let's move on to number 4. So number 4 says the time between arrivals of vehicles at a particular intersection follows an exponential probability distribution with a mean of 12 seconds. So again, even if it didn't say it follows an exponential distribution, typically problems that measure the time between arrivals of something are exponential. Okay, that's the type of distribution we use for measuring time between arrivals or time between events occurring. Okay, and we could look at all these graphs and probably try to figure them out, but honestly, all exponential probability distributions are shaped like this, where they go in a downward curve, and we'll see 12 is at its mean there. All this means, okay, at exponential probability distribution is our probability gets lower the higher our value of X. So even at our mean, right, we'll see that we've expended most of our probability up here, and it gets lower and lower and lower as we go higher with X. So C is the one that is the exponential distribution. So now it wants to know, what's the probability that the arrival time between vehicles is 12 seconds or less? So what information do we know? We know that the probability of our distribution, or the mean, is 12 seconds. Now, when we do exponential probability distributions, we're going to need a number called lambda. Lambda is a Greek letter, okay, and it just means 1 over the mean for these problems. Okay, so now to find the probability that a vehicle, and then we need a value of X. So what is the probability the arrival time between vehicles is 12 seconds? So our value of X is 12. Our mean, it happens to be 12 as well. and then our lambda is 1 over the mean. So now the probability is going to equal exponent for exponential dot dist, where we put in our value of x, comma, our lambda, and then our cumulative is true. So the probability that the arrival time between vehicles is 12 seconds or less is 0.63212. So again, I'm going to have this round for me, so I don't have to worry about making a mistake. C says, what's the probability that the arrival time between vehicles is 6 seconds or less? So all we have to do there is change our x to 6. Once we've created our own little calculator, makes life way easier, 0.3935. What's the probability of 30 or more seconds between vehicle arrivals? So again, we know the probability of it being less or 30 or less is 0.9179. So the probability that it's more is just going to be 1 minus the probability that it's less, 0.0821. Check our work, and hooray. All right, on to the last one. So the last one says, according to a National Association of Colleges and Employers, the 2015 average starting salary for new college graduates in health sciences was $51,541. The average starting salary for new college graduates in business was $53,901. Hooray for business, we're making more. Assume that starting salaries are normally distributed and that the standard deviations for starting salaries for new college graduates in health sciences is 11,000. And the standard deviation for graduates in business is 15,000. All right, so let's set this up. We're going to say health sciences and business. It gives us an average for health sciences as 51,541, and for business as 53,901. Then it gives us a standard deviation for health sciences of 11,000, and for business as 15,000. And so now we have the info we need to do the probability that it's less of something and a probability that it's more. Oh, you know what we need though? We're going to need some value of x. So I'm going to move these down. Okay. So the first one says, what's the probability that a new college graduate in business will earn a starting salary of at least $65,000? So I'm going to come over here and put 65,000 as my x. And then I'm going to use equals norm dot dist with x, comma, mean, comma, standard deviation, comma, true. And that will give me the probability of someone earning 65,000 or less. But this says earning at least 65,000, which is going to be 65,000 or more, right? So I'm going to say this equals 1 minus the probability of less. And this says to 4 decimals. So I'm going to go ahead and make this. It doesn't like that for some reason. Okay. So we're going to say the probability that they make at least 65,000 is 0.2297 or 22.97%. Now it wants the same information for health sciences. So we're going to use the same x, 65,000. And again, we're going to equal a norm dot dist with my value of x, comma, my mean, comma, my standard deviation, comma, and true. Same thing. Probably that it's more will be 1 minus the probability that it is less than that amount. So the probability that it's more than 65,000 for health sciences is 11.06 or 0.1106. All right, what's the probability that a new college graduate in health sciences will earn a starting salary less than 40,000? So to do that, all we do is change our x now to 40,000. And we can see that that probability is 0.1470. And now it says, how much would a new college graduate in business have to earn in order to have a starting salary higher than 99% of all starting salaries for new college graduates in the health sciences? So this one's tricky because it sounds like they're asking me about business, but it's really asking me what the 99th percentile, I guess you would say, of health science majors would make. So remember, to do that, I'm going to find an X of 0.99. Okay. And I'm going to do that by doing norm.inv, the inverse of the regular norm. And for my probability, I'm going to put in 0.99, my mean, my standard deviation. So someone would have to make $77,130. It wants it to the nearest whole number. $77,131 in order to make more than 99% of health science majors. I should say health science graduates. Check our work, and we're all good. I hope that was helpful, and I hope it helps you to work through the rest of the assignment. Have a great week.